Hello, everybody. My name is Dawn Graninger, and I'm actually a postdoc at Lawrence Livermore, and I'm going to tell you a little bit about some of the work that I've been doing in trying to understand how rubble pile structures can actually affect asteroid deflection. And so we've heard a lot today about kinetic impactors, and kinetic impactors are actually one of the most mature methods known for asteroid deflection. And this is achieved through changing the orbit timing and not pushing the body out of the way. We're just going to change the timing so that when the body intersects the Earth's orbit, we're not in the way. And so we will be testing this method with the DART mission. It will be the first demonstration of such a technique. Now, we rely a lot on simulations to try and understand what would happen with one of these events. And so what I'm going to show here, hopefully it plays, is an example of a simulation of an impact into Golvica that Megan showed this morning as well. And we try to calculate this value beta, which we've heard a lot about this morning already. But actually, until recently, we focused mostly exclusively on simulating these bodies as monolithic structures. And that's not actually that realistic because we know asteroids are likely potentially rubble piles. We've known that they should exist since the 1970s. And if we look at the amazing mission results from Hayabusa 2, Hayabusa, and OSIRIS-REx, we can see that there's definitely rubble on the surface of these bodies. And in addition, there's different environments within these bodies. So for example, on Itakawa, we see this nice smooth area of regolith surrounded by an area of boulders. Whereas on Ryugu, it's predicted that there might not even be that much regolith at all. And so it's really important to understand how do these environments affect beta on these surfaces. And so I'm going to talk to you a little bit about our code that was developed by Mike Owen. You heard a little bit about it already, but I will just remind you, I'm using the code Spheral++. It's an adaptive smooth particle hydrodynamics code. It's mesh-free and Lagrangian. And there's a lot of material models and strengths already built into it. In addition, it's open source and can interface very easily with Python. One of the great things about it is actually this novel rubble pile generator that we're going to use, that I use exclusively to try and simulate the effect of an impact into a rubble pile body. And one of the great things about this being an ASPH code is that the fact that we actually use non-symmetric kernels. And so we were able to get cleaner fracture patterns as demonstrated here compared to a regular SPH-based method, and we're able to actually capture ejecta dynamics very well. And so to talk a little bit about how we actually create these boulders in our rubble pile, because it is a little different, I'm just going to walk you through the steps of how we do this. And so first what we do is we create a power law distribution of boulders as defined here. We're using a power law slope of -2.7. And from that power law distribution, we randomly choose a set of boulders between a minimum and maximum size and just sample randomly from that. And so in our case, we're using the minimum boulder size of about 2 meters up to a maximum size of 20 meters. The boulder shapes are then generated using spherical harmonic perturbations. That way you're not creating perfectly spherical boulders. You have some asymmetries in them. And then they're sorted in size and settled down into the asteroid volume. And they basically rappel down from the surface until they hit another boulder. And so here's an example of one of the rubble piles that we generated. Here's the outside view. So you see lots of small boulders on the outside, and you have the larger boulders in the center. But this is by no means the only way we can sort. We choose to sort so that we have the largest boulders interior and the smallest boulders on the exterior. But there's many other ways. You could sort using some sort of random. You can also sort using a Brazil nut type method. And so the obligatory, here are all my simulation parameters. Again, we are modeling a full 3D ellipsoid of the Didymos B shape. Here are the parameters here, and here's an example representation of it. We use a standard Collins pressure-dependent strength for the base asteroid strength with the values for the yield strength and the von Mises. We set a bulk porosity to be 30%. These are the same parameters that Megan presented earlier this morning. But what that works out to be is a 10% boulder porosity and a 50% regolith porosity. We use the granite equation of state using the Tillotson formulation with the values shown here, and we actually evolve the damage in the asteroid. And again, just to reiterate, here are our boulder parameters, with our smallest boulder having a radius of 2 meters and our largest boulder having a radius of 20 meters. Now for our impactor, I'm actually going to present an even different impactor geometry. The geometry I've chosen to use is actually a plate geometry, and it's 1 meter by 1 meter on the edge, but it's only 18 centimeters high. And that way we can use a fully dense aluminum with a mass of 484 grams, and we're having an impact at 6.25 kilometers per second. The reason of the plate is because when you would impact, it's likely any sort of underdense square would crush. And so we try to approximate that using this plate, but still try to achieve the approximate footprint of the DART impactor. And so here's the 4 simulations that I'm going to talk to you a little bit about today. Again, these are full-size rubble pile simulations. We do not scale the Didymos B system. We are actually fully modeling it. And here, and I'm going to be presenting 4 test cases, and they have 5 centimeter resolution and with it at the impact site, and we actually ratio out at a 1% feather. And so it's really hard to see on here, but there is a little tiny red dot that actually represents our impactor, just so you see. And I'm going to be referring to these by their rotation angle, and that's because what I've been able to do is build a single rubble pile, and then what I do is I rotate it about the x-axis, the long axis here. And so that every time I impact, I'm still probing the same bulk boulder properties, the same bulk boulder distribution. I'm just impacting at different representations of it. And that's one of the great things about using this hydrocode is that I'm able to specifically target where I want to impact. And so I'm going to show you here again, we have beta on the y-axis. Here's our time axis, and you can see the evolution of beta. And I drew arrows because it's just easier to see that we see that when we're impacting close to our boulders, we get beta values that are of the highest and also the lowest. Whereas when we're impacting into the more regolith areas, we get beta values that actually seem to be very similar. And we bound our beta between 1.8 and 2.1, which is very reasonable if you think about the different scaling laws. And so we'll start and go through the 2 major cases. First of all, why are these 2 the most similar? It seems very surprising if you're just looking at the data. Why would those be similar? And so we can use the crater fitting algorithm that Mike talked about this morning and look at images of the predicted crater. And so we see as they're nearly spherical, but they often have these boulders on the edges or near to them. And these boulders can obscure the ejecta so that you're not getting things coming out as easily as they would like, but they're not obscuring it so much that it's going to completely block the ejecta coming out. And they seem to have a similar number of boulders near. When you measure the crater widths and diameter, the crater widths and depths of these, they're very similar in crater width and depth. And this could be what caused this sort of intermediate value of beta. Even further, you can see the plate impactor here, and you can see the local environment, and blue represents regolith and yellow represents boulders. And you can see that these are all impacting into mostly regolith. Here are just different cut views of the boulder. And when you impact into the high porosity regolith, it will actually dampen your shock. So you're not getting as much evolution as you would like, so you don't get as much ejecta coming out. And this again could be a reason that we have this sort of intermediate value of beta. Now going back to the extremes of beta, where we have our highest and our lowest, what we see is they're actually impacting close to or actually onto boulders. And so for the maximum value of beta of 2.1, we actually impact perfectly onto a boulder. We center it and it hits nearly, almost, it's very serendipitous, very perfectly on top of it. And you get a perfectly spherical crater. When we use Mike's fitting algorithm, there's very little difference in the widths. You get a width of 11 meters and a depth of 5 meters. And so because this is happening, there's nothing obscuring the ejecta. You're able to let the ejecta plume come out perfectly symmetric, and it will give you the best beta enhancement. Now, if we go to the minimum value of beta of we get a value of 1.8, we actually get a very irregular crater. When we do the hyperboloid fit, there's a whole meter difference between in the crater widths, and the depth is actually very shallow. It's 4 meters. But if you look here, you can see that the center of the crater is not the deepest part of the crater. You can see that it's actually offset. So you're seeing that those boulders, which I will highlight here, which are actually in there, are pushing the impactor into a kind of a weird spot in the crater and causing the ejecta to be obscured. And here is again a top view of it, and you can see the boulders around it and boulders immediately beneath it from this image here. So I just wanted to let you know that beta can be influenced by your local environment. Depending on how your rubble pile is built and where you're impacting to it, you can actually get to, from our simulations, a 15% difference between the beta values, between your minimum and your maximum value. And this is actually consistent with previous 2D simulations that Mike Owen presented at the last PDC, showing that when you impact directly onto a boulder, you are going to get the highest beta. But of course, this is only just 4 different boulder realizations. It would be good to do a larger sample of them, as well as looking at different boulder and regolith porosities. Here I showed a pretty large discrepancy. We had, a 10% boulder porosity and a 50% regolith porosity, but it might not be that's the case, because we've seen from the Hayabusa 2 mission that when they dropped the lander on it, actually was able to crush a boulder. And so maybe we don't want to have such a competent boulder. Again, I'd like to probe a wider range of boulder environments, and of course, also look into how impact angle onto boulders will affect the beta measurements. Thank you.
Okay, questions? All right.
Yeah. Clark Chapman. I think it's really wonderful that we have graduated, or you have helped graduate from identical sized spheres to a power law distribution of constituents of the body, because that is the much more realistic thing. And also they're not spheres as you have generated. I hope that you'll consider varying the power law index and also the maximum size. Mm-hmm. It depends on how comminuted the material was that formed the moon in this case, from being like half the mass of the body down to a very small fraction of the body. A question I have concerns, you have regolith, it seems, dispersed throughout in between the boulders, and the other important case is where it's vacuum, it's macro porosity, and that could be very plausible. We don't see regolith on Bennu and Ryugu, and it may be voids down there that could be big, and if you hit a void, there's going to be a very different result.
Yeah, and so in our code, in our rubble pile generator, we actually have the possibility to do that. I haven't personally looked into that, but I believe that's something that the group is very interested in seeing. If we impact into a pile of boulders, what would happen? And if we fell into, imagine a crevice right between 2 boulders, what's going to happen there? Right. And so that's something we are interested in looking at.
Very good, thanks.
Thank you.
Gonzalo Nacredi. I'm more familiar with the discrete element methods where you simulate the contact mechanics among the particles. Mm-hmm. And I think for the boulder distribution, that is very critical. So how do you simulate the contact mechanics of the particles?
So at the current moment, we simulate our boulders and our regolith, and they do interact just because of the fact that we are using an ASPH method. The kernel will interpolate over both. But if you're talking about how the regolith may rub explicitly against a boulder, that's not something we at the moment are currently.
I'm thinking about the contact forces, the normal forces, the tangential forces, the friction, and all these kind of stuff that it's very relevant for granular material.
Mm-hmm. Yeah, and so at the current moment, I do not believe we are modeling that. I could be corrected by Mike, but I do not believe that's incorporated at the current moment, no.
Okay, at this point, I will turn over the session to my co-chair, Tom Jones.